So our first speaker in this session is Scott Bachman from the National Center for Atmospheric Research and Hewlett-Packard Enterprise, and he will be presenting a paper entitled High Performance Programming and Execution of a Coral Biodiversity Mapping Algorithm Using CHIUW. So Scott, go ahead and take it away.
Oh, thanks, Dan. Yeah, so my name is Scott, and I've been a visiting scholar with the CHIUW team for the last 8 or maybe 9 months. And hopefully, this is going to be sort of a lightweight, not super technical talk, just highlighting something I think is cool that I've been able to do while I'm here. Of course, I'd like to give thanks to my colleagues in the coral conservation community at Coral Reef Alliance in University of Miami, and also special thanks to Ben Harshbarger, who really helped me through the process of making these programs when I was first learning CHIUW. So the backstory is this. I don't know if many of you are aware, but the world has lost over 50% of its coral reefs over the last 30 or so years, and it's projected to lose almost all of the rest over the next 20 or 30 years, due pretty much to human factors. And so one of the things that is a high priority now is creating marine protected areas to physically and politically protect some of the remaining ones. The problem is, where do you put them? Deciding where to put marine protected areas really depends on where you get the most bang for your buck. So for example, where is the most biodiversity? And the challenge is, of course, that going out and measuring biodiversity means you have to travel long distances to these very remote places, doing intensive surveys. It gets very expensive and very difficult. And so the question that sort of is underneath this talk is, can you do this using satellite imagery? Because satellite imagery is cheap, it's repeatable, and it covers a very wide area at high resolution. So can we measure biodiversity from space? So we have satellite images like the one you see here. And the first thing we do is we try to infer what kinds of habitats are implied by that satellite image. So for example, you look at some of these really light blue areas and you think, okay, well, that maybe is a shallow lagoon with a sandy bottom, or some of the darker areas may have coral cover. And so you turn that satellite image into this rasterized habitat map where you say, okay, these are the habitats that are in this image. And in reality, they look like this, right? So sandy bottoms, seagrass, coral, rocky. There's some different types. And so the question when it comes down to measuring biodiversity is, pick a point anywhere on that image and you say, okay, within some distance around that point, this big circle, how many different habitat types are there? Because you'd imagine that each habitat type has its own different types of fish, different types of coral, different types of even bacteria that tend to live there. And the more of those different types and the more of those different habitats that are in that circle gives them more chances to interact, more chances to breed, share genetics. And so it creates more diversity. And this is something that has been observed in the ocean, on land, rainforests. It's pretty much a universal concept in ecology. And so, back to this image, it's really about measuring, how many different habitat types are in this circle and doing that for the entire image. So essentially what we do is we have this rasterized map here. We'll say it's an N by N image. And you have a little mask, which we'll call P by P, which is our circle. And really you're just sort of surveying all the points that are within that circle. Right. So you're convolving that little mask over the entire domain and then doing a little bit of calculation every time you do it. So there's the mask on the image and you're just moving it along, and you do that for every row and every column in the interior of the image. And that's the calculation. It's pretty simple. So the first thing that makes this CHIUW program really quick has not so much to do with the performance of CHIUW itself, but CHIUW did enable this really nice algorithmic improvement to be made. So for example, here's my point, and I've got this blue radius or blue circle around it that represents my little window, and we're asking how many habitats are in that blue circle. So we do that calculation, and then we move one point to the right, just like that convolution implied. And so now, we have this other circle that we're looking at. But the nice trick is that if that new point, you're just stepping one pixel over, that new neighborhood, that new circle pretty much overlaps the previous circle almost completely, except for one little sliver at the new right edge. And so you can actually build the code to take advantage of that. So you don't have to recalculate everything in the circle. And so, every time you step one pixel over, you're keeping the center part, right, that overlaps. You're adding this new sliver on the right side, and then you're just discarding that little bit on the left. And so that immediately saves a factor of p calculations, where p is the diameter of the mask. And so, it reduces the algorithmic complexity by quite a bit, especially because p can be, 100, 1,000. So that immediately makes your program 100 or 1,000 times faster, which is awesome. And so just a quick highlight about how I construct this circular mask. I've taken advantage of Chapel's sparse domain feature, where basically I say, give me a radius and give me sort of an area. And all I'm doing is I'm asking, hey, is this pixel within, this radius of my center pixel? If it is, then add it to the mask. If it's not, then just discard it. And that naturally makes a nice circular mask. So really easy. The sparse subdomains make it really nice too, because then it lets me separate out what's on the left edge, called d_left, what's on the right edge, under d_right. So it makes this really clean to decompose this calculation. And so sort of leaning into that concept, if you think about it, so the only time you're ever calculating the entire circular mask is when you're on the left edge of the image. But then every time you step inside, so step to the right, you're only calculating the right edge, right? So the most expensive calculations happen along the left edge of the image. And so what I can do is I can minimize the number of left edges that each locale has to calculate by simply reshaping my locales. So I'm using a block distribution, and rather than having it create as square of blocks as possible, basically I'm forcing it using the reshape method to make the locales own strips of the image. And so again, it's minimizing the number of left edge calculations. It's making it as fast as possible. And so the nice thing about this is, you don't really, once you allocate a chunk of the image to each locale, it never has to talk to another locale. It just has its own chunk and it just does all its calculations, and that's it. So it's embarrassingly parallel. You can use a co-for-all loop and just chop it up so that, like the previous slide, each locale owns each piece of the image. And then it's a pretty simple computation where you just pass those circular masks, those sparse domains, into a function, and then you calculate this formula, which I've highlighted in the pink. This is called Biodiversity. It has a long history in ecology. But again, with Chapel syntax, really easy, just uses a plus reduce and a little bit of multiplication, and there's your biodiversity. It's really nice. And so just to give you an example of the performance, so again, these are really, really high resolution images. Each pixel represents about 2 square meters. So, 6 feet by 6 feet, that's super high for geophysical data. So here's an example habitat map for Roatan, Honduras. So this image is 11,000 by 4,000. It's a little bit of work to load it up on your desktop. Here you can see all the different habitat types that are inferred from that satellite image. And here is the results after running it through my program. So if I flip back and forth, you can sort of see on the north or top side of the island, you have a couple spots where there's a lot of different colors sort of mashed into one area, and those turn into the hotspots of diversity that you see here in red. And so previously the performance, it took several days to run this. My colleagues were running it using a serial MATLAB code, because that's all they know, right? Because, and I'll tell you, in the science world, it's very common to only learn a little bit of MATLAB or a little bit of Python to get your task done. And sometimes that's the only language you ever learn, because that's sufficient for most people. But for an application like this, people never really learn parallel computing. And so it kind of makes it ripe for something like CHIUW to come in and really speed things up. Yeah, but the computation reduced from days down to seconds, partly due to that new algorithm I was able to put in, and partly due to just the fact that CHIUW, can parallelize and scale its algorithm up as far as I want to go. And people are super excited about this. It's basically legitimized me in the coral reef community. And so I've been able to start a lot of collaborations just in the couple of months that I've had this program in place, and people are just really, really eager to use it. And so just to sort of reiterate, we can do that for different habitat types. They have, say, what they call geomorphic habitats. So you can see up here in the legend, you have land, reef slope, sheltered reef slope, reef crest, et cetera, et cetera. You can calculate biodiversity using any of these types. And, this algorithm isn't specific to, just corals. You could use it on land. It's very generalizable. So, we could do it for other things too. So, next steps, we've done this for Roatan, which is pictured here. And they were asking, okay, well, now it's so fast, we can do it for the whole world, right? So they wanted to try a bigger region. And so now they sent me the entire Mesoamerican reef, which is about 400 times bigger. And it's doable. We actually did it. It only took, not 2 seconds. It took 4 minutes this time, which is still amazingly fast. But the challenge is that now, I'll just flip back to this slide. Now the image is about 20 gigabytes. It's literally impossible to load up on your desktop. So, it's actually a memory management problem now. And so I had to add in some more tricks like, okay, rather than loading the entire image on one locale and then broadcasting it to all the others, now I have to do a distributed read where each locale only reads its own chunk. And so you never have to overload any one locale's memory. And so the big code block here is just, again, using some CHIUW methods like expand and local subdomain to basically tell each locale, hey, go to this part of the input file, just read this, and then you're good. And so visually what it looks like.
So Scott, we have about 3 minutes left if you want to try and wrap up so we can take questions.
Got it. Okay, so imagine this image is broken up into 2 locales. Locale 0 is the upper half. Basically, it's going to read in only its part and plus a little red halo around it so it can do its own computations. And so, and also doing a distributed write of the output. The output image is very similar. Here I'm using the netcdf wrapper. And again, it's only writing out its own chunk of the image. And so everything is completely partitioned, embarrassingly parallel. So another next step, there are harder versions of this problem. One's called Spectral Diversity. Very similar. It's just order p squared, more computationally intense. It's really, really hard to do. And so I've developed a couple different solutions where rather than looking at the full map, for example, which takes a full 12 hours, even on hundreds of cores, you can use sparse subdomains to only look at specific sites. So here I'm showing specific dive sites in those red dots. And with Engen and Andy, we're also working on a GPUized version of this algorithm to hopefully go way, way faster and allow us to do the full map. It works. We're still making it faster. But I also, just want to do this as a shout out to the GPU team, and we're going to get there. I think this is going to be a really, really cool application. Just to summarize, this is CHIUW put on a really cool earth science and biology problem. It is embarrassingly parallel and scalable. It's been super fast. People are really excited about it, and I think the encouraging takeaway is that this type of application sort of highlights, there are so many things out there that people, could use scalability and use parallelism. And, CHIUW is just really good for that. I've really enjoyed using it. And, I'm really excited to share it with people in my community. So, all right. Thank you all. Take questions.
Thank you. That was a great talk, Scott. I think we have time for maybe one question. There's at least one in the chat here. Can I ask, how did you export your raster data sets, GeoTIFF, I guess, in your CHIUW program?
Yeah, it's so we use a what is it? He uses GIS imagery, and it uses a Python library called GDAL. It might be a geotiff. I'm not totally sure, but yeah, basically one of my colleagues goes and extracts it off the Allen Coral Atlas, does some pre-processing, and then I pass it through a Python notebook to just manipulate it a little bit so my Chapel program can actually use it. And yeah, so that part's completely separate from Chapel, but it actually takes longer than the Chapel program by a lot.
Okay, I think we need to move on, but others can continue to ask questions in chat. Scott can hopefully engage there. Scott, if you can release your screen share, and Amitha, go ahead and get started.
Good. Thanks, everyone.
Thank you.